So, when we have a carbon-carbon double bond, geometric isomerism only occurs if the two carbon atoms have different atoms or groups of atoms attached to each. So, here is an example of ethene. What we have to do is take a look at the carbons on the double bond one by one. So the pink carbon, does it have two atoms or groups of atoms that are different? So we've got a hydrogen and a hydrogen. Those are the same. If they are the same, then this molecule does not have EZ isomerism. Okay, what if we did this? Let's put a chlorine there. Let's start with the carbon on the right. It has a chlorine and a hydrogen. Are those two atoms the same? No, they are different. So this molecule could have EZ isomerism. It could have it. But both carbons need to be attached to two atoms or groups of atoms that are different. So let's move on to the other carbon here. It's attached to a hydrogen and a hydrogen. These two are the same. So this molecule does not have EZ isomerism. Okay, what if I changed this top left also into a chlorine? Well, let's pick the carbon on the right. Is it attached to two atoms or groups of atoms that are the same? No, they're different. So it could have EZ isomerism, but we need to check the other side. Is this carbon attached to a chlorine and a hydrogen? Are those different? Yes. So this molecule does have EZ isomerism. It has a isomer. Therefore, which isomer are we looking at? So we need to take a look at the two groups of atoms or atoms and assign a priority. The heavier atom, based on its relative mass, is given a higher priority. So chlorine is 1, it's 35.5, and hydrogen is priority 2 because it has a lower mass. And on the left, chlorine is 1, hydrogen is 2. When the two heavy masses, priority 1, are on the same side of the double bond, this is the Z isomer. So this molecule is, how do we name it? Well, we've got ethene 1,2-dichloroethene. And this is the Z isomer. So we put a Z in front. Then what would be the E isomer? Well, the two chlorines must be on the opposite side, like so. So this is the E 1,2-dichloroethene. We can see that the sigma bond has free rotation. I can rotate around the sigma bond. And this is important because if I show you now this molecule over here, and I ask you the question, are these two molecules the same? Well, remember, molecules' bonds are constantly rotating and molecules are vibrating. They have kinetic energy. But if I take a snapshot of these two molecules or froze time, just by looking at it, we would assume that these two molecules are different. Because in the bottom one, the two chlorine atoms are pointing up on the same side, whereas the two chlorine atoms in the above one are pointing in opposite directions. But because there's rotation around the sigma bond, and the bonds rotate, then once the bonds rotate around the sigma bond, the atoms rotate, and we can now see that these two are actually exactly the same. So we can see that there's rotation around the sigma bond. If I were to show you this molecule now, and these two represent a pi bond, and we said the pi bond, there's restricted rotation. If I try to rotate around the pi bond, it just doesn't work. You can't rotate around the pi bond. So if I were to show you this molecule, and now I bring this molecule, and I ask the same question, are these two molecules the same? Well, we would have to rotate bonds to try and make them superimposed on each other. I'm trying to get this chlorine to point up, so I need to rotate, but there's restricted rotation, so I can't rotate. The only way I can turn this molecule into this is to break the bond here, and reattach them. Well, geometric isomerism does not allow that. So no matter what I do, without breaking bonds, these two molecules are not the same. Therefore, they require two different names, even though they are both made up of two carbon atoms, two hydrogen atoms, and two chlorine atoms. They are not the same. One of them, the two bulky groups, the heavy chlorine atoms, are pointing in the same direction, upwards, whereas the bottom one, they are pointing in the opposite direction. So these are geometric isomers, and the alkene, which has two different atoms or groups of atoms across the double bond that are pointing in the same direction, same side, is known as the Z isomer. So this is the Z isomer. The alkene, which contains two atoms or groups of atoms across the double bond, and the bulky groups here are the chlorine atoms. They are in the opposite direction, so this is known as the E isomer.